Hey, ARE and CE 4260. We're continuing our discussion about serviceability, and now I want to talk about deflections. And calculating deflections for reinforced concrete is a little bit complicated because the concrete cracks. But first, before we get into that, let's just do a review of calculating deflections. This would be the stuff that you learned in 3200. And so here we have the load, shear diagram, a moment diagram, and the integral of the moment diagram over M over EI is a slope. So we have the slope here. Okay, so let me use my tablet. And you can see in the load diagram, it also shows a deflected shape. Right there. So you start with the load, then the shear, moment, integrate one more time, you get the slope, and then finally integrate another time and get the deflected shape. What I'd like to talk about though is moment and curvature. You know F equals kx for a spring, right? So you know that. We have something similar, which is moment versus curvature. So this is force versus displacement, and the slope is the spring constant. What we're going to do, we're going to talk about moment versus something called curvature, and that is also linear. And this is something you learned in 3200, but you might not realize you learned it. You know all about M over EI and stuff like that. I'm going to try and explain that. I'm going to back up and we'll talk about what that really is. So first of all, what is curvature? If you look at these two lines, they have the same deflection, or I tried to draw them with the same deflection. But obviously, right, the one on the right is more curved. Do you get a sense for that? We call that curvature. And in calculus class, you learned about curvature, and it's this. That radius is off the top of the slide. Anyway, 1 over the radius is the curvature. The one on the right has a smaller radius, it's more curved. Okay, the one on the left is flatter, it has a larger radius, it's less curved. It's called the curvature. And curvature is approximately the second derivative of the deflected shape. It's not exactly, and it's actually over the square root of 1 plus the slope to the 3/2 power or something like that. But the slopes for structural engineering are very, very small. So curvature is about equal to the second derivative of the deflected shape. Okay, so that's curvature. Something that has a tighter radius is more curved. It has a higher curvature. Well, moment is proportional to curvature, like this. Okay? Moment is linear with respect to curvature, and I've tried this. So, had an experiment. Cut a piece of wood with a known radius. put some steel on it, bent it. I put strain gauges on the top and the bottom of that steel, and calculated the curvature in ways that I'm about to show you, and found out that the moment is linear with the curvature. So if you double the moment, you double the curvature. It's not having the radius because it's like 1 over. It's like 1 over radius. It's some kind of weird relationship. Okay, so you can get the moment diagram, hopefully, right? You get the moment diagram for something, and it turns out the spring constant for curvature is EI. So the curvature times EI is the moment. Okay, so EI is the constant for the curvature. And you actually learned this, if you don't remember it, all the way back in mechanics and materials. It involved all these proofs and neutral axes and that sort of stuff. We don't have time to reproduce the proofs here, but believe me, in the linear elastic range, this is true. The spring constant between moment and curvature is E times I. Well, what that means is the curvature, which is the second derivative, is m over EI. Okay, so you get the moment diagram, then you divide the moment diagram by EI, being careful with your units, and that is the curvature diagram. And moment versus curvature is a big thing in reinforced concrete, especially in research circles. I deal with this all the time. Okay, now let's talk about concrete. So it's hard to see those cracks. Let me highlight those with the pen. So there you go. Your concrete beam is cracking. There's your moment diagram, still WL squared over 8. But can you see that everywhere the beam cracks, it's going to kind of open up, and there's going to be a very concentrated curvature. What this beam will kind of look like when it deflects. Something like that. Everywhere there's a crack, there's going to be, I've exaggerated it, like a kink in the deflection. There'll be highly concentrated curvature everywhere the beam cracks. Can you sort of see when the beam cracks, it's kind of opening like that, and there's a lot of curvature. This is like a lot of deflection or a lot of angle change in a small distance. And so I am imagining the curvature diagram kind of looks like M over EI with some spikes right where it's cracked. So I've tried to draw that below here. So what that means, unfortunately, is everything you've learned in 3200 or anything you look up on the internet or everything you get out of a steel manual is wrong. And so here are some examples. Whenever you get the deflection, it's blah 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 over blah 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 times WL to the fourth over EI, or it's blah 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 times PL to the cube over EI. You can get WPL. What you need to know are E and I to be able to use these formulas. And you've done all this studying, you did all this work. I think maybe a simply supported beam is 5 over 384 WL to the 4th over EI or something like that. So you have all these formulas you want to use, but it doesn't work anymore because the curvature is no longer just M over EI. So what are we going to do? What we're going to do is make an effective moment of inertia. We're going to do transform sections. And so if you remember all the way back to homework 1, I said the only thing out of that homework that you really needed to remember was the transform moment of inertia, and here we go. N is the ratio of E of steel to E of concrete, and if you remember from that, it was about 8. And the equivalent amount of concrete that is equal to the steel is N times the area of steel. Now, here's a kind of a weird thing. So if you're replacing concrete in compression, okay, the tension steel is just N times AS. The compression steel is N minus 1 times AS, because you know the steel is in the beam, so there's no concrete there, and so there's a hole in the concrete. So it's the steel, which is N times AS, but there's no concrete there, so minus the hole that the concrete is not in, so minus AS. So it's N minus 1 times AS. Okay, so you can get this transform cracked moment of inertia for the deflections. But the beam is cracked in this drawing in 4 spots. But it's not cracked everywhere else. So the question is, which moment of inertia are you going to use? The cracked moment of inertia or the gross moment of inertia? And as a quick reminder, the gross moment of inertia for a rectangle, 1/12 bh². So the question is, do you use the cracked moment of inertia, which is over maybe just 4 spots over very small distances, or do you use the gross moment of inertia, which is almost everywhere else in the beam? What would you use? And in case you don't remember, here's the cracked moment of inertia. We did this, N times AS. Okay. And this is the gross moment of inertia. So which one do we use? Do we use the gross moment of inertia or this cracked moment of inertia? And the answer is a weighted average. We're going to average the gross and the cracked transform. So I've asked you to remember this from homework 1. I know it was a long time ago, but you can calculate that. You can calculate BH³ over 12. And what we're going to do is we're going to average those two. Okay? We need some kind of weighted average. Okay. Well, this changed just last year. So up until 2019, this was the formula to make your average. Okay. You take a certain amount times the gross plus a certain factor times the cracked. Okay. And this is how you get the cracked moment of inertia, just my over I. You solve it for m, and Fr is the tensile strength, 7.5 square root f prime c. Okay. And if it's less than cracked, you can't use is greater than the gross moment of inertia. This formula will come out greater than crack sometimes. In these formulae, A stands for applied. It means maximum. What's the maximum moment? So you take the ratio of M crack over M applied. And if MA is less than M crack, you're going to get a number bigger than I gross. That doesn't make sense. If MA is less than M cracked, it's not cracked. When MA is greater than M cracked, then this fraction here becomes less than 1. And in fact, you can think of this pre-2019 equation like this. That alpha be the ratio of M crack over MA. So remember, that's less than 1 if it's cracked, because the applied moment, the denominator, is bigger than the numerator. You cube it, and then this formula up here is just this. It's just alpha times I gross and 1 minus alpha times I crack. Alpha is the percentage that you're weighting. So let's say alpha is 30%. It'll be 30% times I gross and 70% times I crack. And if alpha is greater than 1, it means it's not cracked, so we just use I gross. This totally kind of, it makes sense. It's like when the moment's big, it's more cracked. And so you end up being more towards the crack moment of inertia. But this got changed in 2019. And the new equation is this. Let me get myself out of the way here. If you're less than 2/3 cracked, you use the gross moment of inertia. Before it was if you're less than cracking. So if you get within 1/3 of the cracking moment, you're going to start reducing your moment of inertia. And here's this ugly formula to get the effective moment of inertia. Okay, so it's no longer this like percentage of gross and the remaining percentage of crack. It's now this, where it's a fraction of that's wrong. The numerator is I gross. Sorry, I'll fix that. It's obviously I gross over all that is I effective. Okay, I talked to Dr. Dolan about this, and he said that this equation, this new moment of inertia compared to the old one, will give bigger deflections. Okay, so this new effective moment of inertia in ACI gives a bigger deflection than the old one. And they were saying they're worried about that this formula that we've always been using underpredicts the deflection, so they kind of fixed it. However, for pre-stressed concrete, so those of you who will take pre-stressed concrete next year, they did not adopt this. Pre-stressed concrete still uses this. But anyway, this is what we'll do. But the next question is, not all of the beam is in positive moment. Some of it's in negative moment, some's in positive. And so what we're going to do, because you get a different moment of inertia, a different crack moment of inertia if the bottom's in compression or the top's in the compression, right? Because, in a T-beam, B is like 100 inches in the top, but B is, like 16 inches on the bottom. And so in the negative and the positive regions, you get a different moment of inertia. On top of that, there's a different cracking moment for negative moment and positive moment. And you have a different transform moment of inertia because you don't have the same steel everywhere. And so what you're going to have to do is you're going to calculate this effective moment of inertia at the left end, the middle, and the right. And this moment of inertia is already kind of an average. And then you're going to average those three. We'll cover all of this in an example. Okay? The other thing that complicates deflections in beams is that beams creep. It's time-dependent deflections. And so let's say your beam deflects 1 inch right away. It might deflect an additional 2 inches over the next 5 years. So the total deflection will be 3 inches total. And compression steel stops deflections because steel doesn't creep, only concrete, and creep only happens in compression. So another reason to put compression steel in a beam, and we talked about this, is to reduce creep deflections. And here's the formula. This lambda is a multiplier. It can be up to 2. And this numerator is the multiplying factor, which we'll get in the next slide. Well, let's just do that. So the multiplying factor, in 3 months, you will double your deflection. This is the additional time deflection. In half a year, you get 120% additional deflection. In 1 year, 140% additional. And in 5 years, you get double the initial deflection additional. So it's the initial plus double, so triple. You triple the deflection. Okay, so in 5 years, you triple the deflection. That's a lot. And so you can reduce this multiplier, so this C in the top here, you can reduce that by 1 plus 50 rho prime, where rho prime is just like rho, but it's just a compression steel. Okay. So that is everything about deflections. The rest of it is easiest to learn in example. And what I've done is I've done an example using a 2019 moment of inertia. I'll post that. But what I'm going to do is an example using, that was pre-2019, and I'm going to redo the example using the 2019 moment of inertia, and we'll compare. And Dr. Dolan says we're going to get a bigger deflection using the new moment of inertia. We'll see how much bigger it is, but that will be the next video.